All right. Well, welcome back. I mean, I said we couldn't start without Andrew. As you get older, these bathroom breaks take on greater significance. So without further ado, it gives me great pleasure to introduce Sary Drappeau from Maass L, who will speak to us today on central values of additive twists of mass form L functions. Sary.
Thank you. Can everyone hear me? Is this on? Okay, now it should be on. Is it okay? Is it okay now? Better? Okay, and now? Yes, now it's okay. Thank you. So thanks for the organizer for the opportunity to be here, and to thank you, Andrew, for everything that you do for number theory. I was a postdoc in 2014, and what I'll talk about belongs to the connected component of what I did back then. So it has nothing to do with variable numbers, but it's about automorphic forms, automorphic mass forms. So I'm sorry, but this will look like course 101. I have to introduce some notations to explain what I did with Asbj and Nordentoft, who's a postdoc in Paris Nord. So we generalized and collected. So did a statement which generalized and collected and explained in general terms a phenomenon which was known in some specific situations. So I have to introduce some notations. And so we start with a discrete subgroup plus L2R. So this will be automorphic forms of for GL2. And then, so we'll be interested in this group, H is the upper half plane, and we look at all functions phi from H to C, which are automorphic of weight K, automorphic mass form. K for us will be an integer. So what this means is that phi is smooth on the upper half plane. Automorphic means phi of gamma z is related to phi of z, to phi of z. Phi of gamma z is related to phi of z. And then there is a factor which is of modulus 1 for argument of cz plus d to the power k. So you can think of k as being 0. This will be before the talk, which just means that phi is a function on the quotient of h mod gamma. So, so to be perfectly general, we add in a character here on matrices, but this I won't be focusing a lot about this other factors that we can put here, not in this talk. So gamma being, so C and D are related to gamma, the two numbers downstairs. Gamma is any element of capital gamma. Is the size okay? Okay, thank you. Then there are some other conditions. The second most important one is mass form. What this means is that phi must satisfy a differential equation of order 2. Then there is an eigenvalue, and delta k is closely related to the Laplacian. So this would be the Laplacian on the upper half plane, the usual one. We twisted by a factor term depending on k, which is okay. This one, but never mind. So we won't be using much technical. Okay, I put this because it's the definition, but okay. There's a letter which will appear later. It's related to lambda by this relation. Okay, so we're interested in this function because they generalize. For instance, okay, we'll see some examples, and then hopefully after the example you'll be interested in that, if you weren't already. They have a Fourier expansion. Yes, a Fourier expansion because they are periodic functions, and so we're going to write it as some terms right afterwards, and the Fourier expansion, which has some shape. This is a basis of one periodic function, and then the weight with respect to n depends on y. So it's separated. For functions fn, which are related to Whittaker functions, but never mind that. I won't be focusing too much on it. And I didn't say that yes, there is some growth condition, and phi is not necessarily cuspidal, so there might be two terms in the expansion. Okay, so I don't. Again, there are some specifics if S phi is 1/2, for instance, but this you can look in Ivanet's books, for instance. Okay, so two examples. important examples. The first one is when p of z is y to the k over 2 times another function, then this being a mass form exactly means that f is a holomorphic classical form. The second case, which is even I find more interesting in terms of multiplicative number theory, is the case of a certain specific Eisenstein series. Don't write it down, which is of weight 0. And the important fact with this series is that the Fourier coefficients are the divisor function. Okay, so so these are the main two examples that we like to look at. So this from this Fourier series. So let's build up a L function by summing all the Fourier coefficients for positive n against n to the s. And so this has a functional equation, taking s to 1 minus s. I didn't say how I normalize the an, but okay, there is a way to normalize it so that the functional equation relates s to 1 minus s, which is absolutely convergent for real part of s greater than 1. So for instance, in the second case here, this is just data squared. All right, the screen here is, maybe I can move that. Okay, I might break things if I try to move it, sorry. Yes? Ah, okay, good, perfect. Thank you. Okay, so the objects that I'm interested in are built from this L function by twisting by an additive character. So now we add in another variable, which a priori is real, and you build up exactly the same function by twisting by e of nx. So there are things that I'm not saying. For instance, I didn't say that gamma was a congruence group. I didn't say there were a Hecker operator. So this doesn't necessarily have a Euler product expansion. I'm working in an analytic setting. So yes, so there is no, we don't expect, I mean, in several instances, this has an Euler product due to Hecker theory. And in these cases, we lose multiplicativity by twisting by an additive character. But we can also work with that in a general setting. So this is what we look at. And the question that you might ask is, I give you a value of s, then how does this behave with respect to x as a function of x? So when real part of s is greater than 1, this is continuous function of x to absolute convergence. And it gets interesting when you are able to extend this as a function of s beyond real part of s greater than 1. But we don't know how to do this for any value of x, but we know how to do this for a rational value of x. So as a function of s, this has extends meromorphically. So in particular, it makes sense to consider the function from x rational to the value at a specific number inside the critical strip of that function as a function of x rational. And now there is no expectation to this being a particularly nice function. So Sandro Bettin will later on this week will talk about values of s different than 1/2, or real part of s different than 1/2. Maybe not in these terms, but okay. And I'll be focusing at the central point, 1/2. Because then something funny happens. Is that this, as a function of x in Q, satisfies a lot of symmetries inherited from phi, which were noticed or known in some special case, but now we have a proof which covers, which is pretty much more general. So the main result is that this is a quantum modular form, according to a nomenclature due to Zagier, in the following sense, that it's not continuous per itself, but if you take the difference of two values, one at gamma x and one at x, the same automorphic factor as for phi. So in this case, it's just chi of gamma times the sine of cx. Okay, this is too small. To the k times L phi of x. Then this is actually Hölder continuous. So extends to a 1/2 minus epsilon Hölder continuous function of x in R, and you need to You need to avoid this being infinite. And we also have a theorem, but another result saying what the size. We have an asymptotic estimate on the size of as x goes to infinity, which is useful in some of the applications. This kind of result saying where this the continuity of such a function or differences of such functions. Remark would be far-fetched. Okay, never mind. So why we're interested in this is for results on the value distribution of these functions. And there are two cases where this was analyzed, or many cases where this was analyzed, mainly the two cases that I mentioned earlier. One of them is when phi of z is associated to a holomorphic form, in particular when this is of weight k equals 2, then actually h gamma is constant. So the modulo symbol associated with f and gamma infinity. Okay. When phi is the Eisenstein series that I mentioned there, Eisenstein series of weight 0, then the function, well, this function, you can put divisor function, so it's very elementary function. It was studied by Esterman. It's called Esterman's function. And in this case, this theorem, the special case, the statement of this theorem in more precise terms was obtained by Sandro Bettin in 2016. So what is it good for, such a statement? State one corollary. I'll have only time to speak about one of them, so I'll just corollary. So for this corollary, you take gamma to be the usual gamma SL to Z, and phi to be cuspidal. You can find a variance, standard deviation sigma f, a number, a positive number depending on phi, such that if you take a random rational among all the rationals in 0, 1 of denominator at most q, okay, so there are two q's, so this is a rational, but this is a bound on denominators, which we're going to let tend to infinity. Then the probability that this value normalized, the value taken by L phi, suitably normalized, ends up in any pre-given domain in C. This will converge to the probability that a Gaussian. Yes, so for this phi, all phi are self-dual. So R is actually R. So this is a real number, and when you normalize it suitably, then the probability is that it ends up in certain interval, for instance, is the same as a Gaussian, ending up in the same interval. So this was at least my original motivation to work on this. Basically, just because we have a set of numbers and they behave very erratically when you plot them. So you will want to understand the size, but these questions originate from my work with Sandro on the Esterman's function. So this was known in several other cases, which I now mentioned. So it was known when phi is y to the kf with f holomorphic, but the methods are completely different. So I'll talk about the methods from that, but the methods are completely different. So method of moments, and you use holomorphicity in a very critical way in the argument by work of Petridis-Risager. That was in 2017, and Nordentoft in 2019. So Petridis-Risager was for k equal 2, and Nordentoft had another argument, knew how to treat general k case, but he still made use of holomorphicity in a critical way. Okay, so later, and then another case where it was known was when phi is Eisenstein series, weight 0 as the Esterman function, and this was with Sandro Bettin in about the same time, but now okay. So the publication date is later than this, and the methods again are completely different. And to prove that corollary over there, we have to rely on the methods, mostly the strategy from here. So the limitation that phi is cuspidal is irrelevant. I mean, we can work with phi not cuspidal. It just changes the statement in a more complicated way. So I don't want to do that. But the limitation that gamma is SL2Z, this is more interesting. It should be true without this condition, simply because Petridis-Risager and Nordentoft they have a statement for any gamma. So it should be true for any gamma. So right now we don't know how to do this, but it's work in progress with Andrew again and Jung-Woon Lee from who's at Work Week. So hopefully by next year we'll work it out. So maybe I have time to sketch a very acute argument as to how we prove that this is a 1/2 minus epsilon Hölder continuous function. And then maybe one word on how to deduce the corollary. It's a parameter which tends to infinity. Oh, sorry, it's from this letter. Here Q tends to infinity. So this is here X, you take it at random among all rationals in 0, 1 with denominators at most Q. Yes, yes, of X denominator at most Q. So we extend, we count more and more rationals according, we sort them out by the size of their denominators. That's a natural way to look at rationals. Okay, and this is what we. It's a probability that a real normalized Gaussian, so mean 0, standard deviation 1, uniform counting probability among all rational numbers in 0, 1 with denominator at most Q. There are about Q squared of them, and you can take one of them at random. So I'll sketch a nice argument, which is due to Asbj on how to obtain a theorem in a special case. So it's a very nice argument because it's, well, you'll see why, it's very geometric. But on the other hand, it works only in a special case, and we don't know how to make it work for the other special case. So we have another argument for to work in general case. So this starts with the representation of the L function, the L value, roughly as a constant. So C will be a constant here. The constant will change, but I don't want to be very specific about it. As the Eichler integral, so an integral over from starting from the rational point X to infinity up there of phi of Z dy over Y. Okay, so this is one phi Caspidal, and the integration path is okay, like this. So this is not exactly true. Actually, what we have to do is to express, because you see I've kind of arbitrarily taken the positive n, but you have, when you integrate, you have both positive and negative. So if you want to isolate one of them, okay, it's a mess with hyperbolic, hypergeometric function. It was fun to work on, but I don't want to share with you this pleasure. Yes, so you have this representation, and now we're going to work with a special kind of mass form, the ones of weight 2. So when phi has weight 2, it turns out that you can always write phi as y times d over dz psi, where psi has weight 0, playing with the level raising and level lowering operators. And this has the special property that when you switch from weight 0 to weight 2, or the other way around, the level, well, this is the level raising operator, has precisely this shape. The reason why it's nice is when you input it here, you have L phi of x being constant times the integral of a derivative, a form which is almost exact. Well, okay, so psi is not holomorphic, so otherwise this would be very nice. But when computing h gamma, we can see what's going to happen. So h gamma is what? Is integrating this function on one side from x to infinity, and you subtract from infinity to gamma x. And what you can do is change variable, a difference of two integrals, one from x to infinity, and one which goes from gamma minus 1 infinity to x along a circle. So the line gets transformed into a circle. And if you complete this picture by drawing a line from infinity to gamma minus 1 infinity, you end up with the expression of h gamma, the difference of these two values, as being almost, so L phi of gamma minus 1 infinity, which is a constant, plus the integral along the border of a triangle. And by Stokes' theorem, which was used in this case. So you have to work a bit more than that. And it's a lemma which Asbj knew from a paper of Imamoglu, Duke, Imamoglu and Toth, that this is this value plus, so there are constants on the way, plus the integral on the triangle of the form psi. So you can see why this is nicer, because for instance, it tells you that H gamma is bounded because psi is bounded and the triangle has finite area. And it can tell you that H gamma is 1/2 Hölder continuous. And how do you see this? Well, you're integrating first on this triangle and you subtract the integral along inside that triangle. So what you're really doing is integrating on two areas counting with signs, this one and this one. And you see that when the value x is getting close to x prime, then the area, the difference of the two areas, you can quantify it in terms of this angle over there. Let's call it theta. So area in, which is pi minus that angle. So if you get bored, you can compute this angle, and you will turn out to be somewhere along x minus x prime to the power 1/2. So my nephews are too young to have computed this for me, so we had to do it ourselves. So this will tell you that H gamma is 1/2 Hölder continuous, which is okay. So I like this proof because there are very little technicalities, but it didn't work for odd weight. So if someone has a proof for odd weight, I'd be very happy to see it. So I think I'm out of time. Is that right? Okay, and thank you.
Further questions or comments for Sary?
Komorowski, Emmanuel, in front, yes.
Do you know what happens if you look at just rationals with a fixed denominator that goes to infinity?
So that's a very interesting question. I didn't mention that this problem of distribution of values have an interest when you taking this twist L phi of x and then playing with orthogonality relation, you get the value of the multiplicative twist. And so when you study questions of non-vanishing, this was in a heuristic paper by Mazur and Rubinstein about applications to rank growth in families of elliptic curves, which question where they got same heuristic as Ethan and Chantal, some other denominators, some other authors. So they were interested in this heuristic. You're interested in what happens for fixed Q. But there is no way by dynamical methods that go inside this theorem. There is no way to get fixed Q. Simply because when you apply Euclid algorithm, you change denominators on the way.
Yeah. So sorry, you said it's dynamical methods to do.
Yes.
So you can just do it by length of the continued fraction or something like that?
Yes. So when gamma is SL2Z, this is Sandro's strategy to express L phi of x. So for instance, the first step is H gamma of x. Forget about the automorphy factors, plus L phi of -1 over x. But L phi is periodic. So here you can say that this is minus the Gauss map. So not the same T, the Gauss map applied at x, and then iterate this. And you get a Birkhoff sum of the function H gamma, which is regular. And you can use dynamical methods to study this. And we started, our starting point was the works of Vladi and Vallée.
So is this what you do? You just translate number of steps of the Euclidean algorithm into up to Q. So if you're going to use a different subgroup, you use the same method?
That's what we want to do with Sandro and Zhongwen Li. So there is a map which we learned about very recently, which we called the Bowen series map. So we're trying to learn about this and try to get the dynamical methods to work in this context. So we're working on this. It seems my optimism is fluctuating.
Any other questions or comments? If not, let's thank Sary again.